I wanted to talk a little bit about enthalpy, a topic that you guys are looking at right now in your textbook. So before we talk about that, there are two key terms I think are really important to remember because enthalpy refers to these two terms. So the first thing are these two ideas of exothermic and endothermic reaction. An exothermic reaction is that energy is being released or is produced during that chemical reaction. Now, when you have an exothermic reaction, this reaction might appear hot or warm because it's releasing energy. It could also appear bright or produce noise because those are two other forms of energy that could be released. On the other hand, an endothermic reaction, energy is consumed or used during the chemical reaction. This reaction might appear cold because it is pulling heat from the surroundings. And if it's pulling heat from the surroundings, and say your hands are the surroundings because you're holding this in like a beaker, that means that it's pulling heat from your hands and going into the reaction. And so your hands might feel cold. Now, when we talk about enthalpy, enthalpy can be thought of as the heat or energy associated with a compound. Now, that might not be too important by itself, and it's actually a lot more helpful for us to think about what's called the change in enthalpy. And the change in enthalpy is the difference between the energy of the products and the reactants in a chemical reaction. So when you have your products and reactants, they each have their own amount of energy associated with them by just being. And so the difference between those is what's called our change in enthalpy, and that's represented by what's called a delta H. Now, the best way that I think it is to understand our delta H's is to look at what are called some enthalpy graphs. So I have drawn a couple enthalpy graphs that I have right here. So we have two different graphs. And what I have is, if you look at the graph, there are a couple different things that you should note. Notice that enthalpy is on one side, so how the enthalpy changes. Does it have high enthalpy or low enthalpy? And the course of the reaction. Now notice, as the course of the reaction occurs, reactants are always turning into products. But notice the difference between these two graphs. In the first graph that we have, the graph that is on your left-hand side of the screen, the reactants have really high energy or high enthalpy. And as a reaction occurs and those reactants turn into products, they're actually producing products that have lower energy or lower enthalpy. So we could think of as the difference between those energies is our delta H, that change in enthalpy. On the other hand, here we have reactants, which are low in enthalpy, turning into products that have high enthalpy or high energy. And notice that that delta H is positive. Now, what does that actually mean when we talk about endothermic and exothermic reactions? And that's what these two next slides are going to be talking about. So let's look at our first graph. This is where we had our reactants that were high in energy and our products that were low in energy. This actually refers to an exothermic reaction. If we have reactants that have a large amount of energy, so they have a large amount of enthalpy associated with them, and they produce products that are lower in energy, that change in energy has to go somewhere. And what happens is that that energy is released, and that's like the excess amount. So if you think of something that has a lot of energy, that energy needs to go somewhere in order for it to be lower in energy. Now notice that delta H is negative, and that means that the energy is released. So whether or not delta H is negative or positive is really important, and that tells you whether or not the reaction is endothermic or exothermic. So in this case, delta H is negative, and that means that this is an exothermic reaction. An example of this might be carbon plus oxygen would create carbon dioxide. And notice that I have energy as a reactant. And the reason why I have energy as a reactant is that it is being produced. So if energy is being produced or released, it's going to be a reactant. And I could also say that my delta H, and it's associated with a certain amount of energy. So in this case, I have my delta H equals a negative, and again, that delta H is negative because energy is being released, as 393.5 kilojoules. Now, another way that we could look at this is we can write what's called a thermochemical equation. And all I'm going to do is I'm going to replace that delta H value of kilojoules and actually plug that into the equation for energy. So now what I have is what I have is I have 1 mole of carbon reacts with 1 mole of oxygen. It produces 1 mole of carbon dioxide, and it also produces 393.5 kilojoules of energy. Now notice that I did not put that as a negative sign, and that's because by putting it on the product side of the equation, that automatically means that energy is being released. So I don't put that sign in there when I'm writing out my thermal-chemical equation. So let's take this example and let's kind of look at what it means when the reaction is endothermic or we have an endothermic graph. Now here's what we have. If we look at the course of the reaction, we still have reactants turning into products, but notice that the reactants are really low in energy and the products are really high in energy. And in order for the reactants to produce high energy products, energy has to be put into the system. Energy needs to be consumed, energy needs to be absorbed. And so what we have is we have this energy going into the system, our delta H. So that delta H is positive because energy is required or energy is consumed in order to get those reactants into a higher energy product. An example of this might be that energy, notice on this case my E, which stands for energy, is on the reactant side. Energy plus nitrogen plus oxygen will produce 2 moles of nitrogen monoxide. So notice that energy is on the product side because energy is produced. This reaction could not occur if we did not put some energy into the reaction to start with, because it needs to have higher energy products. Notice that my delta H is positive, so I have my delta H as 180.6 kilojoules. So that is how much energy is required in order to have this reaction occur. Now, again, I could write this as a thermal-chemical equation by replacing my energy with the actual amount of kilojoules that are needed for this reaction. So again, not putting that sign in there because notice I'm putting it as a reactant, which means that energy is required. So I have 180.6 kilojoules plus 1 mole of nitrogen plus 1 mole of oxygen will produce 2 moles of nitrogen monoxide. And so those are the differences between those endothermic and exothermic graphs. And you can use those to understand how much energy is released. So for example, say that you wanted to run a car. Now, in order to run a car, you need a reaction that's going to produce a lot of energy. And that's actually kind of the whole purpose of burning fossil fuels, is that fossil fuels actually produce and release a lot of energy when they combust. And we could actually apply a delta H to that, and we could figure out what is the most bang for your buck. How much energy can we get from a reaction to run a car? Or how much energy can we get in order to heat a house? And so those are the kind of things that this becomes really important. Now, you wouldn't want to try to run a car with an endothermic reaction because that's not going to get the car going. You're just going to have to take energy to do that. You want to produce energy. You want energy to be a product, and you would have energy as a product with an exothermic reaction. And the bigger that delta H, the larger the amount of energy that's released, the more energy that you'll have to use. So those are some ideas with endothermic and exothermic graphs and looking at enthalpy and the change in enthalpy.